We will continue our lecture for the derivation of Navier-Stokes equation. So I tried to recap a little bit from our previous class. So first we are going to. Okay, I'm sorry. Okay, wait a minute. Okay, Assalamualaikum and good evening, good afternoon. So we continue our class for the derivation of Navier-Stokes equation, the most important equation I think for this solution, for this course. Okay, now I try to recap a little bit from the previous class. So in step 3, okay, we are going to analyze the forces. So we have 3 forces, which is the body weight, so mean the weight of the molecule, and then we have force that comes from the pressure created by the fluid flowing on object, and the third one is force regarding to the shear stress that occur from the interaction of molecules on a surface. Okay, so we go for the pressure force first. So we imagine that we have a cube like this to imagine the fluid molecule. So and then because we are representing the force that occur, so we have a center point here, but we alert that to get force we need surface. So we assume that we have a cube control volume like this, and then we assume that the force will come from the left side and the right side, and the equation to force regarding to the existence of the pressure here is P times A. And in our textbook, I think they give you x minus delta x over 2 because this is the location of this surface. So we assume that the coordinate for this location is x. So the coordinates or the location of this surface is x minus by delta x over 2. And this is the x plus delta x over 2 because the difference of distance, the gap here is delta x over 2. So and then we could calculate the pressure regarding to the force is Fp equal to pressure times A, and then we substitute the value that we have on the x-axis. So because this is the force that occur at x-axis, and we have 2 forces, and you know when we have 2 forces, so we need to add them. So the movement from the right to the left is the negative sign, so we have a negative sign here, and then we could take the value of A, the surface here outside the bracket because it is a constant, so we give it as delta x times delta y. And then if we do this for all the surface, mean surface of y, surface of z, and then we could finally sum them into one term, so it can be like this. So we have delta p over delta x, so times delta x, delta y, and delta z. So and then to simplify this one, if you repeat all of these, so finally we could write this term, and so we simplify this one, so finally we could say that force, pressure force can be written is minus nabla p delta x, delta y, and delta z. So nabla here is actually the symbol representing the formation of del over del x, del over del y, and del over del z. So we have notes about nabla at the end of these topics. So the physical interpretation of the gradient can be right for this one is the net pressure force on a particle divided by the volume of the particle. So because we are calculating for the 3D, so we take all the surface that give effect to this one, so it will become volume of the particle. So then we need to analyze also the shear force, mean the force that comes out of the shear stress. Okay, this one, this idea is actually explained to you in previous chapter. Because we have one condition called no slip condition, where the molecule stick very hard on a surface, then it will create force. Because as you know, if the molecule stick very hard on the surface, if you need certain force to move that plate. So why we need certain force to push or to pull that plate lubricated with something, with fluid, because that fluid hold the plate with certain force, so that the shear force from the molecule there will create force. So because we are dealing with the shear stress here, so it can be simplified that we are using the idea of shear stress tensor here by using this idea. So means that we have, for example, we have one molecule here with a certain shear stress. So we could say that the shear stress can be defined into 3 axes, because we are going to derive this equation into 3 axes, x, y, and z. So we have the tau in yy direction, tau in yz, and tau in yx. Okay, so this is so I just not simplify this work. So at least what we do is actually we calculate all the shear stress on the surface, and then we multiply we sum all the shear stress, and then we multiply with its own surface. Then because we have a 3D there, so sometimes we have x, y, and then y, z, and and then we have zx to represent the area. Then if we factor them all, we could say that it can the equation will become like this. So it will multiply with the volume x times y and times z. So and then we simplify that one. So finally, this is the final terms. So the shear stress can be simplified as nabla of shear stress times the volume. So, and then as the physical meanings, it can be said that the net shear force on a fluid particle divided by the volume of the particle. So it also can be said that it is the total shear stress that acts on a certain particle, and it's divided by its own area actually, but in mathematics, when we sum all of them, so it will become the volume of the particle. Then what we already derived about the pressure force and shear force, and what we need to do now is we substitute all the value that we have in previous calculation into our basic Newton's second law of motion, mean F is equal to ma. So we substitute the value of mass with rho and volume, and then we expand the term of acceleration here with dv over dt. So we substitute the weight here, and then the pressure force and the shear force. So we substitute with all the terms that we get previously, and then to simplify them, okay, we could cancel out the value of volume here. So and then the terms here can be simplified as this one. So means this rho dV over dt is equal rho g minus nabla pressure P plus nabla shear stress tau. Okay, the problem here is we still not calculate the value of shear stress, because shear stress is actually as I said, the simple ideas of shear stress is the strength of molecules, holes, or stick on a surface. So that the idea of shear stress in this context. So the previous calculation is actually proposed by Navier, okay, one scientist, and then in 1845 there is another scientist named Stokes. So he proposed to calculate the value of shear stress here by using the idea of density and viscosity. So we learned about viscosity, shear stress, torque, and so on and so forth. So why density is become a part of this calculation? Because we have two types of viscosity, as you know. So we are dynamic viscosity, we have kinematic viscosity. That's why the density will comes into the calculation. So what Stokes do is Stokes propose the idea how to calculate the shear stress by using the equation. That's why this final equation will become Navier-Stokes equation. So we simplify that one, and then we could say that the above calculation here so can be written off. We substitute the value of nabla here by as I said, nabla is the symbol of certain mathematical function. So nabla here is actually del x, del y, and del z. And then we substitute the value of tau here with the shear stress that occur on x-axis. So because we have x, y, and z axis, so we have three terms of this equation. So we substitute the value of nabla here, and then Stokes proposed to change to substitute the value of tau here with this term. So and then he do another analysis, and then he could simplify that actually the tau xx is actually is equal to 2 mu del u del x, and tau yy is here, and tau zz is here. But for tau xy and tau yx, it's actually the mu del u over del y plus del x over del. And I'm sorry, this is not del x, this is del u over del x. Okay. Okay, this is actually del v, I think. Okay. Yes?
Okay, sir. V.
It should be v here. Okay, I made mistake. Okay. Okay. So and then what Stokes did is actually Stokes put all the equation that we have here into the previous idea of this one, and then it could be simplified like this. So this is the final version. Okay, this is the version that Stokes substitute all the ideas of that one. So it will become, for x momentum, it will become rho du dt equal rho gx minus del p over del x plus mu and all of this term. And for y momentum, so we have all of this term, and for the z momentum, so we have these terms. But you need to understand that because we will analyze in three-dimensional, so you need to remember all of these terms. So for x momentum, for example, I try to give you hint the difference between x, y, and z. So if in x momentum, so it will refer on the u velocity. So, and then we have y is v and z is w. And then again, because the basic calculation here, we have a gravity here. So please write the terms for the gravity. And this is gravity that acts on x-axis, and this is gravity that acts on y-axis and z-axis. And for sure, in real calculation means when you solve this problem, we could assume that gravity on x and z gravity is equal to 0 because the gravity only works on y-axis. Okay, and then you could see it's focused on x axis here, y and z depend on the axis that we take the equation. Okay, and for this one, so for x momentum, as I said, it focused to the u, so everything here is u and everything here is v for y momentum, and everything is w for the z momentum here. And because the equation here is a little bit longer, it's long, so some mathematician will simplify this one into this one. So in some, according to my observation, there is, it is common for a textbook to write down this term as Navier-Stokes equation, because you need to know the idea of nabla P and also the nabla square V. Okay, why this become a nabla square? Because if you see here, so we have a del over del x by the power of 2, del square over del y square plus del square over del z square. So the nabla itself is actually about the del over del x plus del over del y plus del over del z. So because all of this term has quadratic value here, so it will become nabla square here. So so and for in official terms, we could say this one is the Laplacian of the velocity field. So this is the very general Navier-Stokes equation that you need to remember. Okay, so then so here why we use capital V, because capital V is actually always equal to the component. Capital V is the summation, means the resultant velocity of its component. So we could say that capital V here is actually consists of U plus V plus W. Okay. So this is the meaning of Navier-Stokes equation. So as I said, Navier-Stokes equation is actually one equation that tells us everything. It is complete. It is can be used for incompressible and can be used for compressible. So rho dVdt is the mass of the particle. So rho dVdt is the mass of the particle times acceleration of the particle divided by the volume of the particle. And rho g is actually about the weight of the particle itself. And then the delta nabla P is the net pressure force, and mu nabla square V is actually the net of the shear force. Okay, and then the dimension of this Navier-Stokes equation is kilogram over meter square times second square, because the idea is actually the force divided by the volume. Okay, now that is this one is actually the general terms for Navier-Stokes equation. But when we solve problem, we are not using this one, because the symbol of nabla and the symbol of capital V here is actually need to be expanded. So then I hope you could understand that you need to remember this equation. These three equations, so this is for x-axis, this is for y-axis, and this is for z-axis. So you could see the difference. And again here, if you realize that in this term we use capital D and capital V, so the meaning of capital D here is actually the summation of del dt, del x, del y, and del z. And then the capital V there is actually the value of velocity of u. Okay, so that's why we have the simplified version is like this. But the most important thing is you need to understand it, you need to remember, and you need to capable to write down the Navier-Stokes equation for this one. If you could remember one of these, so it is you could use for write the equation for y-axis and z-axis. Okay, so this is notes I already upload in my website. So this is the revision, the Cartesian coordinate for continuity equation. So we already discussed this one, and I also put the continuity of polar coordinate. So we have this one. So we will go through this today. So and then this is the Navier-Stokes equation for Cartesian coordinates, because after this we will see the Cartesian, the Navier-Stokes equation for polar coordinate. So this is the notes for the capital D dt. So it is actually the symbol for this one. So we don't have this one. That's why for if you are going to analyze something in x direction, so means that you put a u here, because u is the velocity in x direction. So and then you need to put all u here. So that's because the equation is long. So that's why mathematician it simplifies it as a lambda. And the simplified as the capital D here, and the lambda actually the simplifies for del over del x plus del over del y and del over del z. So and then in certain textbooks, sometimes they will give you a certain organization, or they organize a little bit. They rearrange the location of the equation to describe Navier-Stokes equation. That's why some textbook they will give you difference, and might be in certain solution they will give you another version of Navier-Stokes equation. So the common one is actually, because we have rho here, sometimes they divide all the equation here with rho. So then we could have, there are no rho in the left side, and also there are no rho in the right side. But if you want to cancel a rho here, you need to have 1 over rho at this term and also for this term. And at some textbooks, they will say that because mu over rho is actually equal to nu, mu is the dynamic viscosity and rho is the density, and they could change this term into nu. So please be careful when you read about Navier-Stokes equation, because it will give you, might be 1 or 2 version of Navier-Stokes equation. You need to understand all of them is actually correct and can be used for your calculation. Okay, so this is the Navier-Stokes, the notes, the notes for the symbol, and this is the Navier-Stokes for x direction. So this is the Navier-Stokes for the y, and this is the Navier-Stokes for the z axis. Okay, so and then we are going to see, just go through, because we are not going to have idea of energy. So the energy is actually, we have this idea. So the conservation of energy is actually in Bernoulli equation for incompressible flow is actually can be used, but if you do in simulation and so on, you need a very specific term for the energy. So this term is actually, so dE dt is actually the rate of change of energy in the system. So, and this is actually about the energy that occur, or in control volume plus the energy that occur, the changes of energy that occur in the control surface. So what is control volume and the control surface here? So the control volume is actually what happened inside a system. So for example, if you have a balloon, so the increment of mass and so on is actually a part of energy changes might be that occur inside that volume if you have a balloon. So, but at the same time, when the balloon expands, so means that the surface of that balloon is increasing. So it means there is certain changes of energy occur on the surface. So because that is the idea. Okay, the idea of this one is actually I think you already learn about Reynolds transport theorem. So this is the idea of Reynolds transport theorem, or sometimes they call this about the integral methods. Okay. So we just go through this one. Okay. So the idea is the same. We have a control volume here. So we assume that we have the idea a cube one, and then we have energy at inlet, and we have the energy at outlet for our control volume. So and then the idea is simple. So what we need to do is actually because we have x, y, and z axis, so we just determine the idea of energy at inlet for x, y, and z, and then we have the energy flow at outlet here. So and then we sum of them, so we will get this one. So I'm very fast here because the normally people for master level they are using for the Navier-Stokes equation to describe the velocity and pressure. So the energy for the differential form is actually more in thermodynamics, because when we want to analyze about the heat dissipation and so on and so forth, they will use the idea of this one. So it's because the calculation of this one will use the idea of K, which is the thermal conductivity of the fluid. So normally in fluid, in UTM, we divide the idea of, so in fluid, we assume that there is no energy release, so means that the energy only convert from the potential to the kinetic only. It is not involved the energy that release as heat and so on and so forth. So if you see, so we calculate everything here. So I just go through here. So finally, we have the idea of this one, which is the equations for this one. So you have rho CV dt over dt equal K nabla square T plus phi. Okay, wait a minute. Okay, is that okay for you?
So what is that fee?
What?
That fee, what is it? Stand for what?
Okay, phi is actually the something about heat, I think. I will check for this one, because for heat transfer, so might be I'm also not very sure about this actually.
Okay.
Okay, I will tell you later. As I said, normally for fluid, we are focusing in continuity and Navier-Stokes equation, momentum.
Okay.
Okay, so for thermodynamics, they will use all of these parameters.
Okay.
Okay. So for our syllabus, we are focusing on continuity equation and Navier-Stokes equation.